I am not Engin Karakioglu. I am Daniel. Engin unfortunately got snowed in during yesterday's storm, and so if I look like I'm partially reading off these slides, I am. I first got to see them yesterday, and I'm going to do my best here for you. Yeah, I think we'd better kick off. So I'll start talking about what Chapel is. So I do know how to talk about that. Chapel is a programming language developed currently primarily at Hewlett Packard Enterprise, or HPE, that is intended to be parallel and scalable. So the idea for Chapel is to support various forms of parallelism, including multiple cores, GPUs, and distributed deployments on supercomputers. It's also portable, and when I say portable, I really mean Linux and Mac OS, so Unix-based systems. We've tested on the Windows subsystem for Linux, and we've also run on various platforms, including various networking technologies such as InfiniBand, slingshots, and just plain Ethernet cables on Raspberry Pis. And Chapel is a general-purpose programming language. It's not really a DSL for anything in particular. It really is meant to be a full programming language to develop various applications in. It's been used already in fields including aerodynamics, data and graph analytics, and various earth science fields. Chapel is intended to be a modern programming language, and so we have object-oriented programming, memory and type safety, error handling. Recently, we've had a lot of work in our tool and IDE support. So you really are intended to be programming Chapel like you would program Python or something else. And finally, Chapel is an open source programming language. We're a member of the High Performance Software Foundation, and therefore the Linux Foundation. And now I guess I'm going to give you a little bit of a taste of the appeal of Chapel. So here I have, I believe, the Stream Triad benchmark from HPCC. And what I have on screen right now is the implementation using C, MPI, and OpenMP. So you can see these are actually two slide screenshots that are inserted in this slide. And on these slides themselves, there are multiple columns of the code that implements the Stream Triad benchmark. And as you can see, the font's really small. You're really not supposed to be able to read these. The idea, though, is that with Chapel, most of this can be reduced to mysterious falling object. Most of this can be reduced to a handful of lines of code. And I don't think I'm going to go through them here, but actually, I guess I will. Here we're creating a distributed array, initializing 2 of these distributed arrays with predefined values, and writing a computation, well, pretty much the expression for stream, in a single line of code. Actually, these are 2 benchmarks. Hi, I lied to you. There's also a different benchmark here, which is the random access benchmark. And here as well, the key portion of the code is just a couple of lines of code. And the cool part about this is that the scales, here I have some graphs of scaling of these up to 256 nodes. And in fact, in the random access benchmark, it looks like the MPI performance flattens out, whereas Chapel continues to scale linearly throughout. So now I guess I got to talk about various applications written in Chapel. They range from hundreds of lines to programs that are about 150,000 or over 150,000 lines of code. These have been run on regular workstations, single GPUs, commodity clusters, and leadership class supercomputers. So some of the examples of this work are an analysis of coral reef biodiversity using satellite imagery, so I haven't seen this, but a Monte Carlo simulation of light transport in tissue, CHAMPS, which is a pretty large open source Chapel code base, I think it's open source. Actually, I'm not sure. But it's a aerodynamics modeling, and yeah, multi-physics simulation is what they describe themselves as. And Arcuda, which is covered here by the QR code, which you can scan to learn more. But Arcuda is a distributed data science library powered by Chapel, but available through Python. So in the last year, we have taken on efforts to become part of the HPSF. This is why I'm here. This is why Engin was supposed to be here and will be here, I trust, a few days from now, or at least hopefully tomorrow or today. So as part of these efforts, we formed a technical steering committee and we've created a public repo which tracks all of the information for all of the notes and discussions that we've had in public. We've also created a governance structure and became an established HPSF project. We opened our weekly project meetings, which we've been having for years, to the public, and as a fun little bonus, we changed our logo, which you can see on the slide now. OK, so I've been talking about all the ways you can use Chapel, and I've shown you some Chapel code, but I guess now I get to show you a little bit more. And in fact, I get to step you through the model that underlies Chapel and its parallel and GPU programming abilities. So here on the slide, I have a couple of nodes diagrammed as these little boxes, which have CPU cores, you can see in purple and pink, and memory, which you can see in blue. The gear being in a particular square represents that particular core running some computation. And the A and little rectangles in the memory represent data. So here I have a 10-element array A, and I have a serial loop which just increments every single element in the array. This is just a regular for loop. It does pretty much exactly what you'd expect. But with a small change to a parallel loop, which is a for all loop in Chapel, this becomes a parallel loop. So by default, this is just running over all the CPU cores on a single node. And so here, A is still stored in the memory of one node, but all the cores available to that node are running the computation. Now, if you wanted to do a little bit more work and actually distribute this computation across multiple nodes, you would use a distribution. And there's many distributions to use because there's many ways to distribute your data across nodes. Here I'm using the block distribution, which creates chunks of the array and splits those chunks as evenly as possible across various nodes. So here, there's only 2 nodes, and the 4 rectangles representing the array are now split evenly between node 0 and node 1. And the for all loop, without changing, is now running a parallel computation over all these nodes and all of the cores available to them. And OK, well, this turning back to a loop on a single node without distributing the array, I guess what I'm going to talk about now is the features that in Chapel unify the way that you do parallel computation or distributed computation and GPU computation. And this feature is a notion of locales. So a locale is kind of an abstract notion of a computing resource. So this computing resource has some memory and some ability to perform computation. And in many cases, this is just a single node. But there's other ways to partition and to think about computing resources and memory. So for instance, on a single node, you might have several locales if you have a couple of NUMA domains, and then you want memory to be accessed by from the right NUMA domain, basically. Similarly, you might want to have a locale per network socket or per GPU, because GPUs effectively have their own memory and computing resources. So thinking about them as a sort of separate thing is helpful. So here, as I alluded to earlier, GPUs are represented as their own little nodes or their own little, well, we call them locales. They're sublocales because logically a GPU exists within a particular node as opposed to being its own thing that you have to communicate with the network. And of course, in the Chapel programming language, there's a number of constructs that are available to reason about locales, including the variable here, which tells you where you currently are, an array of locales, which tells you all the nodes available to your program. And this can be the size of your current allocation, say. And of course, for any particular locale, there's also a subarray of GPU sublocales. So let's kind of, now that we know about locales, let's go kind of step through this a second time. So the idea here is that using an on statement, which is a single construct in Chapel, you can transfer an execution to a different locale. So here, the execution is transferred to locales 1, and since arrays are in Chapel 0 indexed, this is the second node. I guess they're nicely 0 indexed here as well. So instead of running a parallel computation on locale 0, which is by default where computation starts, the computation instead occurs on a different node. And so with this 2 line of code, because you need the closing brace at the bottom, you've transferred execution to a different node. If I then instead transfer execution to a GPU sublocale, I can run the same parallel loop on the GPU. And so here, The array A will be allocated in GPU memory, which you can see because A is in the memory of the little GPU 0. And the for all loop will perform the increment on the GPU. And this kind of highlights the strength of this model, which effectively allows you to use very much the same code to reason about distributed and GPU-accelerated computations. And like I mentioned earlier, here is a variable that tells you where your current computation takes place. And here starts with 0. So since no other code transfers to a different node, changing the previous locales 1 to locales to here causes the original GPU to be using this code. So of course, so far I've only showed using one particular GPU on one particular node, and what you probably want is to run these computations on all nodes and all GPUs. And the first step to that is a co-for-all loop, which runs a parallel task for every iteration of its body. So it's basically used to set up batches of several things running at once. Here, for every GPU available on the node, I'm then transferring execution to that GPU, and because each part of this loop body here is executed in parallel, this concurrently transitions execution to all GPUs, and then executing the kernel. So now every GPU is getting an array of 10 elements allocated on it and running the incrementation kernel. We can also clean this up a little bit by using a do keyword, which is just helping you strip a little bit of curly braces from your code. And then to make this work on all GPUs on all nodes, we simply add another co-for-all loop, which goes over all the available nodes in your system. And so here we have a parallel loop over all locales, and then transfer execution to that locale. And then for every GPU on that locale or on that node, we perform the kernel. Yes, great. So now this is potentially a little bit boring because all I've done so far is made more computing resources do the exact same work, like 10 times. So now I'm incrementing the same array 4 times. So to do this in a better way, we want to split that work across all these resources and only do parts of that work. So here, we allocate the whole array of 10 elements on the first node. This is the CPU array here in the first line. And within the body of these 2 parallel loops, of these 2 co-for-all loops, we copy the data local to that array. We copy like that particular locale's chunk of the work, which is represented by the myChunk variable and is omitted in the slide for brevity. So we copy that particular subset of the work of the array into a local variable and then perform the loop. And this way, we're effectively distributing the computation or the incrementing of CPU array across all locales and all nodes, or all GPUs and all nodes, and doing it in parallel. The Chapel team is actively looking to grow the programming languages community, and we're interested in folks to come talk to us, basically. So if you would like to do that, you can go to our website, which is down here. And then I suppose that QR code is probably taking you there as well, though I cannot say for sure that I know. And the community subpage has a number of ways to engage with us. It's also a tab linked from the community. It's also linked from the navigation bar of the website anywhere you are on it. We're active on a number of platforms. I'm not going to read them out. I think this list is pretty complete. So if you're engaged with projects on these platforms, feel free to reach out. And to learn Chapel, we have a number of various learning resources on YouTube and also on the Chapel blog, which I don't see listed here. And if you have an idea for how to apply Chapel or a library that you'd like to see come to life, the Chapel team is currently looking for things to apply Chapel to. And there is a public GitHub issue or GitHub discussion, kind of the same thing, honestly, where you can go and talk to us as well and suggest ways that the programming language can be used for your domain. So the link is down here. I trust that the QR code also goes there. Once again, I haven't verified this. And now I've arrived at the conclusion. So as I mentioned, Chapel is a parallel, scalable, portable, and open source programming language. It allows its users to easily prototype their applications on a laptop and run it on a supercomputer because of the same exact model being used for parallelism kind of in a unified manner. Chapel, because it's a high-level programming language with a number of niceties, allows you to onboard new developers with different backgrounds fairly easily. And like I just mentioned, you can use the same code to work on a number of different architectures. I probably should have drawn attention to this, but I didn't ever say what type of GPUs were running in that example with the multiple nodes. And that's because in Chapel, you don't really have to care about the underlying provider. We currently support NVIDIA and AMD GPUs, and the same code will work for both. So there's a number of existing users currently applying Chapel to their work. You can read on the blog a series called The 7 Questions for Chapel Users, where we simply interview people about things that they've done with Chapel. There's so many various use cases that I simply have not had the chance, or I'm simply not going to read them all out loud to you, and I think you're going to get pretty bored. But you can scan this QR code and read more if you want. You can also contact Engin, not me, through this LinkedIn link down here. And I believe that's it. I think I have time for questions. Thank you. Go ahead.
Can you talk a little bit to your experience in onboarding in HPSF? You know, how was that transition going? What kind of challenges you guys ran into or not?
This is difficult. I wish that Engin was here to answer that question because he was more involved with that process than I am. I think that it's certainly the case that we were not very experienced with the legal aspects of transferring to a foundation. You know, like Chapel has been an open source project forever, and we've been uploading releases and engaging with users. But things like transferring like a trademark or something like that and going through these kinds of reviews is just something that we're not familiar with. From my understanding, which like I said earlier is a little bit limited, it was kind of smooth sailing with the HPSF and Linux Foundation law team to draft all these sorts of things. So from what I can tell, those that have engaged with us were pretty pleased. Go ahead.
Could you comment on the change of name? There was some discussion about changing the name of the project.
Yeah, there was. The Chapel programming language, the name Chapel, came from the Cascade High Productivity language, and some of the team members feel that it has like needless religious connotations, and we were just looking into other potential names. And there's a couple of things here, like the effort for transitioning a whole project's name, and also picking a name that everyone likes. There was a major candidate, and then it turned out that was too close to other established trademarks, and so that kind of candidate kind of fell short, and no other one was close to having that support. So for the time being, it sounds like we'll be called Chapel. Oh, there's, yeah, please.
So I'm just wondering, so can you talk a little bit about mixing Chapel with other languages and any challenges debugging, misbehaviors in one or the other?
Yeah, so Chapel primarily mixes with other languages through foreign function interface interop, a lot through C and C++, or mostly C, basically, but so you can run Chapel programs in like a regular old debugger. So if you have problems that like are segmentation faults or something like that, you can troubleshoot that fairly easily. There's been recent work done to kind of play nicer with these debuggers in many ways. So like we are a different programming language, and those debuggers aren't really as aware of us as they are of C and C++. So the moment you cross the boundary into Chapel code, things start to look a little bit weird from a debugger's perspective. But we've been making progress on improving that in particular, and also on kind of optimizing at the right level to enable you to see the problems that you're seeing, but at the same time, have debug information instead of just reading plain compiled code in GDB, say. That's all I personally know about foreign function interface. So I know that we've interfaced with Fortran, C, and others, but I do not know as much about the actual troubleshooting of these approaches. Jade might be able to comment more.
I encourage you to come to my talk on Wednesday, where I will be demoing a whole bunch of interrupts in Chapel, including C, Fortran, and HIP. So, also MPI. Not with MPI, just limited time, but we can. I haven't written it. To be honest, I would rather write Chapel than MPI, and so I really do not write a lot of MPI. I know there's a lot of MPI code out there, but that's not my expertise.
My question was around that, like, what's the story around, like, interoperability? For example, solver libraries, right? Like, the big solver libraries are all, like, C, C++, with MPI, right? And maybe different program and whatnot, right?
That is a great, NPI interrupts a great question for anything.
I will say that kind of the models between Chapel and MPI are slightly different. So when you're writing Chapel code, you're writing a single, like logically a single thing that happens and then splits out into different tasks. Whereas my understanding is that MPI is multiple concurrent things that are interacting with each other. And so, like, naively, I can foresee challenges interacting between these two things just because their models are so different. But like Jade said, Engin would be the person to to really weigh in on this. Go ahead.
Compiler, do you leverage like LLVM optimization, like go to LLVMIR or how does your compiler work?
Yeah, so historically the compiler generated C code, but we've been moving away from that too for a long while now. Since I've joined the project, LLVM has been the default backend. So we support both. Using the C compiler traditionally has been, or the C backend has been nicer because you can read the C code better. And like if you're in a debugger, there's the source mapping to the C code, and you can kind of figure out what's going on. I believe there's been recent strides with debug information in LLVM as well, so maybe you don't have to do that as often anymore. But yeah, we use basically traditional LLVM. We boil down our code, which we have like our own intermediate representation at first because we have to reason about distributed systems, memory that might living on a different node or something like that. But then in the end, it all boils down to LLVMIR, and so we can leverage LLVM to compile to various platforms. LLVM is also how we do our GPU interop. So LLVM fortunately has backends for CUDA and HIP or AMD, and so we are able to lean on that quite heavily. I don't actually know when this session ends. So stop me if I'm taking too long. But also, if there are any other questions, please. Yeah, let me go. Oh, yeah, that's far back, huh? This-ish? To be perfectly honest with you, I'm not certain. Oh, Jade. Okay, great. Go ahead, Jade.
The reason that bottom graph is much better is we map much better to the hardware primitives than MPI is able to in that benchmark, specifically the remote atomics of the NIC itself, which is why that graph does so much better. In particular, and that in particular, when you run on InfiniBand, you see very different results on different networks, just based on how the library is mapped down to.
Thank you.
graph is quite impressive.
And thanks, Jade. And we just got our 1-minute warning, so if we have other questions, you could please direct them to me and Jade during breaks or just after this. Thanks very much for listening and for talking. Thank you.